Hi, welcome to Unit 5. This is for Astronomy 1000. Today we're going to be talking about the night sky and specifically about the celestial sphere and why is it so useful. And we will list some reference points on the celestial sphere, explain the nightly motion or the daily motion of objects in the celestial sphere, because believe it or not, even during daytime, objects move still in the celestial sphere, and then estimate the position of objects based on their coordinates and what kind of coordinates we use in the celestial sphere. So again, what we usually talk about celestial sphere is more like, honestly, is a kind of a dome, because we can't see the entire celestial sphere because of the horizon, because of the Earth, okay? So in this case, I have an object in here on the celestial sphere. When he looks up north and south, east and west, the maximum we'll see is his horizon or her horizon. And then anything above is half of a sphere. That's the dome that he's going to see. The extension of that on the other side is going to be the celestial sphere. Okay, is it real? No, it's not. Is it useful? Obviously it is, to understand where objects are and also predict their location, to locate objects in the sky and also make some predictions in the future based on past histories. There is an element of depth that is missing from the elements, the celestial sphere. And that is, if I have two objects, one closer than the other object, when I look at them projected on the celestial sphere, they look like they are on the same level. Right? So we can't really have that much detail in terms of the distance of objects from us, but we have other ways of finding these things, and that's the purpose of other units down the road. Objects in the sky, they appear to form shapes. Those shapes, they fall into two classifications, either constellations or asteroids. So what's the difference? Constellations are named objects and they have boundaries. We know exactly what they are. Asteroids, on the other hand, are shapes that help you recognize stuff in the night sky. One of the famous constellations, of course, is Leo in here, and this is how the stars of Leo would appear in the night sky when you look at them. For you, they may look different. People agreed that they look like some sort of a lion, and that's basically what this constellation is named. And also, asterism, on the other hand, is a group of stars that form a well-known shape that you can recognize. Case in point, for example, is Orion's belt, which are three stars inside Orion's constellation that you can recognize once you see them and you say, oh, that's a line. That's actually, I mean a line. I don't mean this line. I mean like a straight object in here. And those are Orion's belt. Or another well-known asterism, for example, is the winter asterism, made up of three stars that form a triangle, almost an equilateral, and those are Betelgeuse, Procyon, and Ceres. So those three stars, they form, at least in the northern hemisphere in the winter, and they are a well-known shape. Okay, so that's a distinction. There are more constellations in here. This is how Cygnus will appear. This is how it's represented. As I said before, there are 88 named constellations. You don't really need to know all of them, okay? You don't need to know all of the constellations, but it's a good idea to be familiar with some of them, or at least some of the asterisms, okay? They help you find objects in the sky. For example, the northern star, which helps you in your navigation, or for that, at least for our northern hemisphere, it's visible all the time, at least in the night sky, as long as there are no clouds, of course. Okay. These are some of the objects that we need to be familiar with when we look at the sky. Okay. Obviously, when you are in the North Pole and when you look straight up, that's your zenith. By the way, wherever you are, doesn't have to be in the northern hemisphere. If you look straight up above your head, that is your zenith. The opposite of that is the nadir, okay? So those are two opposite directions. If you happen to be on the northern hemisphere, your zenith will be the North Pole. I mean, the North Celestial Pole, I should say. And the nadir will be your South Celestial Pole, okay? There is a star in here that hovers just very close from the North Celestial Sphere, and that is actually Polaris, or the Northern Star, okay? All objects appear to be moving east to west on a regular basis, including the sun during daytime, the moon also, planets, stars, galaxies, if you happen to, or at least clusters of stars. And they rise and set on a regular basis. The objects that are very close from the north celestial pole, they appear to be moving in circles, though. Okay, case in point, for example, Cassiopeia. Okay, goes all the way and then makes a full circle around its axis, 24 hours basically. You have to track it day and night. But if you happen to see it at night, you will see that it makes a good chunk of a big arc of a circle around the northern star. And that's due to the rotation of the Earth. Earth spins from west to east. Objects appear to rise from east to west. That's basically, in a nutshell, what it is. The Earth equator that divides the north from the south is, if you project it in the sky, becomes the celestial equator. And then your horizon, and that depends on your location, is again the extension of all of your surface all the way to the end until where the sky meets the Earth, basically. That's your horizon. Okay, it's a local object. Okay. So these are some of the terminology that are used for the celestial sphere. If you happen to be on water in the ocean, for example, or a big lake, your horizon will extend in all directions. Okay. And that's actually a good place to see everything. You have north, south, east, west, depending if you are in the northern hemisphere and you're looking due south and extend your hand, the right hand will be to the west and the left hand will be to the east. If you look due north, then again, the thing flips. Your right hand will be to the east and your left hand will be to the west. Okay. If you happen to be in the northern hemisphere, exactly at the northern hemisphere, and you look down, up, that's going to be your Polaris, the North Star. Okay. If you happen to be on the equator of the Earth, the North Star will not be on your zenith, but it's going to be on your horizon. Okay. So that's basically, if you happen to be like we are here in Southern California at 34 degrees, the North Star is going to make 34 degrees from the horizon or 56 degrees from your zenith. So depending on your point of reference and how you measure things. Objects on the Earth are measured using two coordinates. Okay? They are the latitude and they start at the equator. If you go due north, you can go as far as 90 degrees, positive 90 degrees that is the northern hemisphere. If you go due south, that you're going to go all the way to negative 90 degrees. So there is a span of 180 degrees from negative 90 all the way to positive 90. Okay. If you happen to go from east to west, though, we have longitude. The longitude is measured from a conventional point, conventional reference, and that conventional reference passes through the city of Greenwich in England. That's where the observatory was. That's when they were deciding where to start reference. So they said, okay, start from here. And then passes through Europe, Africa, and then a good chunk of the Atlantic Ocean. And then on the other side, there is the dateline, which we're going to be seeing down the road when it comes to time zones and things like that. So that extends from north to south pole and comes back to the north pole. Anything west of that can go all the way to 180 when it meets the dateline on the opposite side. Then anything that goes from east side goes from 0 to all the way to 180 again to where the dateline is. The dateline is basically where tomorrow is starting and today is ending, or yesterday ended and today started. So that's basically what the convention for that is. The opposite of the prime meridian on the other side. So it has a span of 180 plus 180, that's 360 degrees. That's basically what the longitude is. Any object on the Earth in here will have specific coordinates, longitude and latitude. Obviously, there is another element in here that we're not including, and that is the element of height, but that's really very small compared to this distance. Okay. If you project that to the sky, you will find how we locate objects on the sky too. Instead of using the latitude, we use the declination. So the declination is similar. It goes from the celestial equator all the way to the North Pole, positive 90 degrees. North celestial pole, I should say. And then the South celestial pole goes all the way to negative 90 degrees. There is a difference though. Instead of longitude, we have the right ascension. The right ascension is not measured in degrees, it's measured actually in hours. And it starts from a conventional starting point all the way to 24 hours. Basically, the coordinates are measured in hours, arc minutes, and arc second. How many arc minutes in an hour? 60. How many arc seconds in an arc minute? It's 60. Similar to how the clock works. Okay. The key point in here, these are measurements of angles. So you're asking, how many degrees is an hour? Well, it's easy. 360 degrees is a full circle. 24 hours is a full circle. Divide 360 by 24, you should find 15 degrees of right ascension. Of declination on longitude on Earth would correspond to right ascension in the sky. So that's basically how we locate objects in the sky. Okay. So this ends Unit 5. Thank you.